Thank you.
And next speaker, Anastasia Molchanova from Institute for Spectroscopy. Investigation of luminescence manganese centers in yttrium aluminium borate single crystals.
Good afternoon, dear colleagues. I would like to present you a work which was carried out mainly in Institute of Spectroscopy, Russian Academy of Sciences, but some part of this work was performed in National Research Center Kurchatov Institute and in Scientific Center Crystallography and Photonics RAN. This work is devoted to investigation of manganese luminescent centers in yttrium aluminate borate crystal. Manganese as dopant and co-dopant can be included in different compounds with different valences. 2+, 3+, and 4+. And these compounds exhibit wide range emission, depends on crystal field and chemical surrounding. These compounds can be used such laser media, light emitting diodes, near-infrared phosphors for different medical application, and others. Our work is devoted to investigation of manganese centers in yttrium aluminate borate. Yttrium aluminate borate doped with different rare earth and transition metal ions are well-known phosphors for different applications such display panels, laser media, and effective eye-friendly microchips. This compound has a structure of a hantite mineral, which is presented on figure. And in the structure, manganese ions can be coordinated in a different position, which is depend on its valence and ionic radii. Manganese 4+ can replace aluminium ions in slightly distorted oxygen octahedra. And manganese 3+ and 2+ ions can replace yttrium ions in trigonal prisms. It's important to note that both yttrium and aluminium are trivalent in this compound, so the presence of manganese in different valences raise issue about charge compensation. Recently, optical spectra were investigated by other authors from Kerensky Institute of Physics. Absorption and luminescence spectra were measured at room temperature, and our lines of manganese 4+ were registered and investigated their polarization dependence. And they were made an assumption about crystal field parameters of manganese 4+. Possible manganese 2+ lines are observed. So the possible scenario of the formation of charge compensation dimers was proposed. We decided to continue investigation of valence state of manganese in investigated crystal by X-ray absorption spectroscopy. These measures were performed in Kurchatov Institute, synchrotron radiation source, and local coordination were studied by fitting XF spectra near manganese KH. And fitting revealed parameters of distances between absorbing atoms and neighboring atoms. And the conclusion was that manganese can replace by fitting an Yttrium positions. A valence state was investigated by a fingerprint method, comparison manganese spectra at KH with a spectra of manganese reference in different valences, 2+, 3+, and 4+. As we can see, 2+ is shown a good agreement. So the presence of manganese 2+ ions in the structure in Yttrium position were established. In our laboratory, we investigated optical spectra, absorption, and luminescence. Okay. Absorption and luminescence spectra. This is our laboratory experimental equipment based on Fourier spectrometer Bruker IFS 125, which can measure spectra in a wide range from terahertz to UV with very good spectral resolution. This setup is equipped by 2 helium closed cycle cryostat, so we can measure spectra in a wide temperature range too. The slide presents the temperature dependence luminescent spectra in a red spectral range. On the spectra, we can observe narrow lines, which are lines of manganese 4+, the same as in chromium 3+. This spectra corresponding to transition from excited doublet to E to ground state 4A2 in manganese 4+ ions. Excited states doublet is splitting by crystal field, so we can observe R1 and R2 lines. Usually these lines characterized by well temperature dependencies, distribution of the intensity according to the Boltzmann distribution. The same picture we can observe in our case. We observed our lines not only in luminescence but in absorption spectra too. And the slide presents such spectra at low temperature of 5 kelvins. Near zero phonon lines, we observed white bands corresponding to vibronic bands of these transitions. As can be seen, our two lines is splitted, which is maybe due to presence of manganese Fab4+ ions in a slightly distorted position with a different crystal field. Photoluminescence decay time were measured for airlines, and it is 1 millisecond for room temperature. An interesting result of our work is presence of near-infrared low-temperature luminescence. It has form of a splitted zero phonon line and white vibronic sideband. This pattern was observed for a number of different manganese 3+ doped garnets, and these lines of these transitions has different energy location. This bands was assigned to transition of manganese 3+ ions between two excited states triplet, spin-forbidden transition. The energy of these levels are dependence, has the same dependence on crystal field, so corresponding energy position of lines of these transitions are the same for all investigated compounds. In more high frequency range, we can observe more wide bands up to 80 wave numbers. And we assigned these bands to spin-forbidden transition in manganese 3+ ions from excited triplet to ground Yttrium splitting doublet. If you look on whole spectra, we can see the wide band from 9,000 to 18,000 wave numbers which observed in whole temperature range. This band is correspond to spin-allowed transition of manganese 3+ from excited states triplet to Yttrium splitted doublet ground state. This is a well-known band of luminescence band of manganese 3+ ions, which is usually is very sensitive to temperature, and so some manganese 3+ ions, compounds with manganese 3+ ions can used as thermoluminescence sensors. First attempts to determine different manganese 4+ and 3+ centers were performed, and photoluminescence excitation spectra were measured. The emission wavelengths were the wavelengths of the most intense manganese 4+ and manganese 3+ ions. As we can see, the excitation spectra are different, but for more clearly understanding, it's necessary to perform such experiments by laser selective spectroscopy method. In conclusion, the valence states of manganese luminescent center in yttrium aluminum borate was performed, and by method of X-ray absorption spectroscopy and optical spectroscopy. And valences of manganese ions are 2+, 3+, and 4+. Our lines were observed in both of absorption and luminescence spectra, as well as manganese 4+ lines of same transition, a slightly distortion position of manganese. Near infrared luminescence of manganese 3+ ions were observed, transition between free excited states triplets, and broadband manganese 3+ luminescence were observed for whole spectrum and temperature ranges. Thank you for your attention.
Thank you very much. Have your questions?
Можно спросить?
Можно.
Анастасия, спасибо. Вот на одной картинке было, что совпадают линии поглощения и линии люминесценции, бисфононные линии. Это так или не так? Что нет сдвига, да, в люминесценции никакого относительно поглощения?
Да, линии совпадают, просто есть небольшое отличие по интенсивности линий.
Это нормально? Нормально такое совпадение? Никакого сдвига нету, да?
Что еще раз?
Это нормально, да? Вот мне казалось, должен быть какой-то сдвиг все же между поглощением и люминесценцией.
Ну, мы такого не наблюдали, но, возможно, стоит провести еще более какие-то подробные измерения, потому что линии очень сильно зависят от температуры, и надо еще раз провести измерения, чтобы внимательно проследить, чтобы температура спектров поглощения и люминесценции, чтобы вот они были совпадающими, и тогда уже точно можно было сделать вывод.
Ну, это, по-моему, такой довольно принципиальный вопрос, ну, это с моей стороны. Ну, хорошо, понятно. То есть у вас прямо на спектре все совпадало. Поглощение и люминесценция, бисфононная линия. Я так понял, по крайней мере.
Бисфононные линии, да.
Вот это да. Спасибо, да. Ну, надо разобраться, да.
Добрый день, спасибо большое за интересный доклад. Вот если я правильно поняла, по расщеплению этих вот линий во втором выводе, вы делаете такой вывод о том, что часть ионов присутствует в локальном окружении, ну вот distorted local position, правильно я поняла?
Да, да.
И при этом во временах затухания вы не видите никакого вклада вот этих вот ионов в другой локальной позиции? Или вы за этим не охотились?
Ну, во-первых, время затухания было измерено не самым чувствительным методом, то есть это надо будет перемерить, а во-вторых, оно мерилось только для линий, которые совершенно однозначно относятся к 4-валентному марганцу.
Понятно, хорошо.
Вот, так что, ну, это мы тоже собираемся сделать.
Спасибо большое.
Спасибо.
Коллеги, еще один последний вопрос. Вопросов нет. Thank you very much. Есть.
Скажите, пожалуйста, вот у вас была кинетическая кривая показана, затухание люминесценции, и она немножко отклонялась от экспоненты. С чем это связано?
Ну, это в логарифмической шкале.
Вот это. В логарифмической видно, что немножко отклоняется здесь в эту сторону, а там в эту сторону. Не прямая.
Я думаю, что это просто связано с тем, что, может быть, с шумами и с тем, что это не очень точное на данный момент измерение. Ну, как-то более подробно я не могу на этот вопрос ответить. Вам спасибо.
Спасибо.